All right, so the next thing that we're going to do is writing Lewis dot formulas. And so we're going to put more than two atoms together, and we're going to make molecules of different sizes. And so a Lewis electron dot structure is a two-dimensional representation of the electrons in a molecule. So what we're going to do is represent bonding electrons. So kind of what we already saw. Bonding electrons will be indicated either by two dots or by a dash. So again, I prefer a dash because it's a little less cluttered. But then unshared pairs or lone pairs will be also shown on the structure, and we do put those in as dots. So how we go about writing these electron dot structures, or I guess formulas, I usually call them Lewis dot structures. These are going to be the rules or the guidelines to help us write electron dot structures, even when the central atom doesn't follow the octet rule. So what we'll find out is some atoms don't follow the octet rule, but we're going to account for that. So we're just going to, I think the easiest way to do that is to just do an example. So what we're going to do is we're going to draw the structure for PCl3, and I'm going to go through each guideline and tell you what I'm talking about as we do it. So PCl3. The first thing we want to do is we want to find out the total number of valence electrons that the molecule has. So it's kind of like this. It's kind of like a puzzle. So the phosphorus and each of the three chlorines come to the table with their given number of electrons, and they want to figure out how they can share these electrons so that they're all happy. It's kind of like I said, kind of like a puzzle. And so how many electrons do they each bring? Well, we saw that earlier already. They're the valence electrons. So remember, they're the same as the A column numbers. So phosphorus is in the 5th column, and so it has 5 valence electrons. And each chlorine is in the 7A column, and so it has 7. Now there's 3 of them, so we have to multiply by 3. So this will be 21, 5 plus 21, and 26 electrons. So the total number of valence electrons in this molecule is 26, and they can't have any more or any less than that number of electrons. And so they kind of want to figure out how all of them can each have 8 electrons with the 26 that are present. So again, yep, 5 electrons from the phosphorus, 7 each for each chlorine times 3, so 26 total electrons. So that's the first step. You want to know how many valence electrons the compound you're trying to draw has. Now, if you have a polyatomic ion, remember that a negative charge means it has an extra electron. So we have to add the charge to the total to get the total number. But if there is if it's a polyatomic cation, that means, remember, if it's positive, it means it's lost an electron. So we have to subtract the number of positive charges. So let's just do an example. So for example, in O3 negative, nitrogen is in the 5th column. Each oxygen is the 6th column, so 3 times 6. And then we have to add 1 more for that negative charge. So that'll be 18, 22, 1, 2, 3, 24. If we had a cation, so for example, NH4 plus, we need to subtract for every positive charge. So nitrogen plus 4 hydrogen, and then we want to subtract 1 for that, so that'll give us 8. So that's the first step, finding the valence electrons. All right, then what we're going to do is arrange the atoms radially. So we put the least electronegative atom in the center. Generally, it's the one that's listed first. At this point, if it's going to be something different, I'll kind of give you some little hint, like put both of those in the middle or whatever, you know. So generally speaking, if it's one element with a few others, put the first one in the center. And then what we're going to do is we're going to make a bond between each element and the ones in the outer circle. Now, each bond, of course, means that we have used up 2 electrons. So let me come up here. So we had, what did we say? We had 26 electrons. Right now, we've used up 6 electrons already just making the bond. So now we have 20 more electrons that we can use. So then step 3 says to distribute the remaining electrons to the peripheral atoms first. And we want to satisfy the octet rule. Now this is kind of important. Don't put them to why I have this saying the peripheral atoms first is what we'll find out is that the center atom can often have some of the exceptions. So it's often the central atom that'll make multiple bonds or might have extra electrons or might have fewer electrons. And so we kind of want to leave the central atom to the end to see what has to happen. So what we're going to do is we're going to give the outermost elements electrons first and then see where we are. So in this case, if we put those 6 more, so remember, just keep in mind that hydrogen only needs 2. So once hydrogen makes a bond, it doesn't need any more. But anyway, in this case, chlorine needs 6 more. Each chlorine needs 6 more. So how many have I used? I've used 18 more electrons. So I still have 2 electrons left. So then step 4 says distribute any remaining electrons to the central atom. So an interesting thing to keep in mind is that the central atom can have up to 12 electrons. But it must have 8, but can have up to. Okay, so in this case, so remember we said we had 26, and then to make the 3 bonds, we lost 6 electrons, and then to give the electrons to all the chlorines, now we have 2 left, so that means the 2 electrons will go right there on phosphorus. And then what you want to do is go back and make sure everybody's happy. So this chlorine has 2, 4, 6, 8. Again, that's 2. This chlorine, 2, 4, 6, 8. This chlorine, 2, 4, 6, 8. And the phosphorus has 2, 4, 6. And those 2 make 8. So they have to have at least 8. And so once they have 8, we're good. All right, so let's do another example for this compound, SCl2. So again, we have 20 valence electrons. How do we get that? Sulfur is in the 6th column, 6A, and each chlorine, there's chlorines in the 7th column, so 2 times 7, which is 14, and so that's where the 20 comes from. So again, we start by putting the S in the middle and make bonds to each of the chlorines. We've used up 4 electrons to make those bonds, so we have 16 left. The next thing we want to do is give the peripheral elements their 8 electrons. And so 2, 4, 6, 8, 10, 12, we've used up 12 more electrons, and we have 4 left. The 4 go on the center atom. And now we have 0 left, and then we want to go back and make sure they all have 8. And in fact, chlorine has 2, 4, 6, 8. Sulfur has 2, 4, 6, 8, and chlorine has 2, 4, 6, 8. So everybody's happy, and this is the Lewis dot structure for SCl2. So it just kind of reviewing. So chlorine has 1 shared pair and 3 unshared pairs. Each chlorine does. Sulfur has 2 shared pairs and 2 unshared pairs. So that's going to be important later, but for right now, let's just keep going. All right, here's one more example, COCl2. Now in this case, they're different. Still, the first one is generally the one that's placed in the center, and it's the least electronegative of all of them. So what we're going to do is put C in the center and surround it by 1 O and 2 Cl's. Now again, 24 electrons, where does that come from? Carbon's in the 4th column, oxygen's in the 6th, and each chlorine is 7, so that's a 14, so 24. All right, so let's put the carbon in the center. Now, does it matter where I put the O's and the Cl's? Let me draw this over here. I just happened to do this because I kind of know the structure, but if you wanted to do it like this as well. There's 3, so that's why it's kind of triangular. But keep in mind that Lewis dot structures are only 2-dimensional, so it's not it doesn't matter how you did them. So if you wanted to do it like that, here I've got it as a triangle. What if instead I had the chlorine down here instead? It really doesn't matter. You kind of want to make it sort of square-like in a way because 8, 2, 4, 6, 8, we tend to use a square, but here I just happened to put it as a triangle because I knew there were 3 things being attached. But anyway, it's not critical if the O was here or the O was down here or whatever. But anyway, the first thing I want to do is make my bonds between the elements. So I've used up 2, 4, 6, so I have 18 left. Again, I want to put I need 8 for all my peripheral elements, so I put 6 around each chlorine, 6 around oxygen, and I have 0 left. So most of the time students will say, okay, I'm done, good. But remember, the last thing you have to do is double check to make sure that all the elements have at least 8 electrons. Otherwise, they're not happy. Like I said, there's 1 or 2 exceptions that we'll talk about in a little bit. Hydrogen, of course, being one of the big exceptions. And actually boron, beryllium and boron can actually be exceptions, but I'll mention that later. Anyway, most all other elements want to have 8. So if you notice here, carbon only has 6, 2, 4, 6. It's not happy. Chlorine's happy, oxygen's happy, they're all happy, but carbon's not happy. So what happens when you have 0 electrons left to give, but one of the elements doesn't have all its electrons, 1 or 2 of them? What we have to do is make a multiple bond. So in this case, oxygen is going to share electrons with the carbon. So instead of giving all 6 unshared pairs to oxygen, okay, we're continuing. Yeah, there's what happens is that oxygen gives 1 pair back to carbon, and now we have a double bond. So a double bond, remember each bond is 4 electrons, so now carbon has 2, 4, 6, 8, and oxygen still has 2, 4, 6, 8, so it still has it, and the chlorine's having the single bond. Now you may say, why did you make the double bond to O and not the Cl's? If you go back a few slides, remember I said what the common number of bonds that certain elements, now it's not absolute, but it kind of can help you. So oxygen tends to like to make 2 bonds, and so that's why I picked oxygen. Chlorine really doesn't like to make 2 bonds. If you think about it, it only really needed 1 more electron to fill, so it prefers to just make single bonds, and oxygen will do a double bond, so that's why I picked oxygen. And so now the octet rule is obeyed. Let's do one more example. Cn negative. So again, it's a -1, so we have to remember to add 1 electron. So carbon has 4, nitrogen has 5, and then there's 1 more electron because it's negative, so that's a total of 10 electrons. Here we go. So that's, I should write it like this for the negative charge. Okay, so let's go ahead, start out the carbon and the nitrogen. So I made a bond between them. So I used, so there were 10 electrons, and just to make this bond right here, I'll just make it thick. To make that bond, I used 2 electrons. So then what I did is I gave, as kind of like, whoa, well, and there's no necessarily, well, let me put it this way, there's more than one right answer here. So I happened to, since I had 8, I kind of split the difference, and I put 4 on the carbon and 4 on the nitrogen. At this point, it wouldn't really matter if you wanted to do it this way. Because the molecule's not happy anyway, we can't stop here. So at this point, either one of these answers would probably be okay, but we're not finished yet. So we've used up all the electrons. So 2, 4, 6, 8, 10. We've put all the electrons, but actually in this case, neither carbon nor nitrogen are happy. If we look at this one, we can see carbon's happy, but nitrogen's still lacking 4 electrons. So again, if there are missing electrons, that means they're going to have to be a multiple bond and share. So if I'm working, let's see, let's do that. Okay, so what I did here is I took 2 of the electrons away from carbon and made a double bond. You can see now nitrogen, and in this example, nitrogen now has 8, but carbon only has 6. Now, probably if I were doing it again, both ways are correct. I might have done it this way. If I had started with this one, I probably would have made 1 double bond. And now this time, carbon has 8 and nitrogen only has 6. But either way is correct, because we're not at my final answer yet. So clearly, we still have to make another multiple bond because the carbon doesn't have enough in this sequence here. So if I share 1 more pair of electrons, so I've shared one of nitrogen's electrons, so now it's a triple bond, so carbon has 8 electrons and nitrogen has 8 electrons. When it is an ion, it's kind of common, it's correct Lewis dot structure, what you call protocol, to write the charge kind of over to the right of the Lewis structure. Okay, sometimes we get into a situation where we don't know what to do. This is an example of a delocalized bond or a resonance structure. It turns out that this molecule, this is ozone, can be represented either way. Now, what's the difference between them? Not much. You can see on the left-hand side, the double bonds on the left and the single bonds on the right, whereas on the right-hand structure, the double bonds on the right and the single bonds on the left. Now, you might say, well, can't you just draw it one way or the other? Well, no, because if you actually did a study on this structure, what you would find out is that these 2 bonds are equal to each other. So it's kind of like there's not a double bond and a single bond. It's kind of like each bond is about 1.5 bonds. So let me kind of go through how I would do this structure from scratch. Let's see, let's go to the next slide. Okay, this is one way that we can represent a resonance structure, is that it's kind of like I said, 1.5 bonds each. Let me go ahead and draw this one for you and go through the process. I think it's helpful. So ozone is 3 oxygens. In this case, it doesn't matter. You just put 1 in the center. And since each oxygen has 6 electrons, then 6 times 3 is 18. So I have 18 electrons. I'm just going to draw it straight so that you can sort of see another view of it. Okay, so I have 18 electrons. I've just drawn my bond, so I've used up 4. So I have 14 electrons. Again, using my rules, I want to give all the outer atoms 8 electrons. Sorry. So I've used up 2, 4, 6, 8, 10, 12. So I still have 2 more electrons. So what do? I put them on the center. So that's what the structure looked like before I put the multiple bond. And I know that this can't be the correct molecule because, or the correct Lewis structure, because the center atom doesn't have 8, it only has 6. So I know that I need a multiple bond. So one of the 2 outer elements has to donate 2 electrons to the center atom. So the last time we did an example, a few slides back, we had the choice between oxygen and chlorine, and I said, well, we picked oxygen because oxygen tends to like to make 2 bonds and chlorine doesn't. So that one was easy. In this case, what happens is I have the same element. So, you know, there's nothing saying that this oxygen is more likely to give electrons than this oxygen. So when you have a choice and you can't make a choice or make a decision between them, what you're going to do is what I just said. You're going to draw the resonance structure, and what I would do, let's take those away. I'm going to make the double bond to that oxygen, but I'm also going to draw a second structure where I'm going to take the double bond electrons from the other side. So, so the best answer is to draw them both. And generally what we do is we put a double arrow between them. I could have drawn them side by side and drawn a double arrow between them that way. Now this is another way to represent it, but we generally draw the resonance structures like this. So if there comes an example, and we'll be doing some in lab, if you have to take a double bond, like one double bond, and there's more than one option and they're all identical to each other, all the options are the same, then you want to draw. So if I had a third one, I would draw a third structure to a third oxygen. So just depending on how many you have. So again, it's called delocalized bonding. It's kind of like both oxygens are sharing, it's kind of like they're both sharing 1 electron, but we can't make a bond with 1 electron. So it's kind of like they're each sharing 1.5 bonds. Again, so here's what I said with the arrow. Now it just happened that I drew this one triangular, which you'll see in a little while that is the actual shape of it. So that's kind of given more of a shape to the molecule, but at this point it doesn't matter if you draw it straight out or not. So usually what we'll do is we'll draw the structure with the double bond to one side, draw it with the double bond to the other side, and put a double arrow. And like I said, if there happened to be a third oxygen, let's say there was, I know it's not real, but let's say there was a third oxygen up here, and we would just then draw a third structure with the double bond going to the third oxygen. So however many of that same element you have, you make that many structures.